Okay, yeah, thanks Sydney, thanks Hussein for having me again. I don't have to change the title, that's nice, State of Containers. Even though I kicked out Linux containers because now you can do Windows containers as well, but that's another topic. I put the slides there on Google Docs, so you can just type in this link there and it will forward you to the slides. So if you want to follow or if you want to do it afterwards, just kniep.org Lugano 2018. I'm very creative with my URLs. Yeah, so this is I've lost count, like the fourth iteration of this talk, and I will give a brief introduction about containers, and we did this along a couple of times, so it will be very short. And then I will also explain the architecture a bit and piggybacking on what we heard with Shifter. And at the end, I would like to also talk about the convergence of big data, AI, and HPC, right? And yeah, let's jump right in. So I'm in the HPC, or I grew up in the HPC community, that's fair to say, worked for automotive companies, was in charge of InfiniBand for a big crash test cluster at one German automaker. And afterwards, I switched to work in Paris for Bull, for the Exascale Interconnect. And there I got in touch with Docker. It was version 0.7 back in 2013. So Docker recently had his 5th birthday, and I have my 4th birthday with containers or with Docker. And I used it to spin up my own little HPC data center on my laptop. So I had this idea of creating a little data center on my laptop, starting with virtual machines that didn't went so far, so I put it aside. And when I learned about Docker, I thought I have to look into it, and it proved very nice for putting a lot of little machines, in quotes, on a laptop. And I talked about it in 2014, and then had my first interview with Rich back in the days, and we talked about it there as well. And after I had some years in HPC, there was a conference in China, an HPC Advisory Council conference, where at the end there was a panel, and the question was given to the panelists whether HPC can learn from the cloud or cloud can learn from HPC. And the notion was among all the panelists that HPC cannot learn anything from cloud, and cloud can learn everything from HPC. And I was, okay, what about this Docker thing, Linux container thing? Maybe I should pivot a little bit to look into cloud stacks as well. So I quit my job at Bull and started at a little weird hipster startup in Berlin for half a year. And then I switched to PlayStation Now to containerize their cloud stack. And recently I joined Docker, like last October. So I'm 6 months now technical account manager for Europe, or EMEA for that matter. And the cool thing is that I learned HPC, and I learned the fallacies. I learned that Docker was not ready or was not approaching HPC the way it should approach it. So I don't have any grumpy thoughts about Singularity, Charlie, Cloud, or Shifter. So I'm neutral there. I mean, I'm a little bit biased because I work for Docker, but not too much, I hope. And within Docker, I can now put Cloud and HPC to work and have this joint effort to advocate for you, actually, within Docker, which I think will be beneficial, hopefully, for all of us. So a little technology recap, and I would like to start with a comparison of hypervisor and container virtualization, and we saw this earlier today. Yeah, on the left-hand side, we have traditional virtualization, right? We have a hypervisor, this is a type 2 hypervisor, and we have mimic the same machine underneath in virtual machines here. So we have our application and our user land, and we communicate through multiple layers to get to the hardware eventually. But what really is a little bit of overhead, or even a little bit more overhead, is this piece in the middle. So the kernel within the virtual machine is of no use, and the hypervisor as well, and the user land of the host as well. What you really want to do is you want to run the application on the hardware. So this abstraction is kicked out essentially by containers, because you share the same host kernel, and since everything is Linux anyways, in most of the cases, you can just kick out the abstraction underneath and directly talk to the same host kernels since we have a couple of techniques now in the Linux kernel, which I will show in the next slide. So this is like the light comparison. A different way of looking at it is the interface view. So you have an application, maybe a Python piece of code, and you want to run it on your hardware. What you need is a runtime, some libraries to actually interface with the kernel at the end. So this rectangular shapes are supposed to be syscalls, right? So if you want to interact with the hardware, you have to go through the kernel, and the interface to talk to the kernel is syscalls. And if you have a hypervisor, then you use hypercalls to then go through the hypervisor, and the hypervisor will translate everything into hardware calls and talk to the hardware. On the right-hand side, we have containers, and containers, as said, they use the same host kernel as everyone else. There's only one kernel in the way, so you don't have scheduling problems between the guest kernel and the host kernel, because there's only one who knows everything about the applications running on the system. And also a cool thing is that the application and the libraries are independent from all the other services that are running on the system. So you don't need to have your application and your library worry about syslog or SSH daemon or slurm daemon or whatever within this userland. You can just run your application, and you don't have to worry about other services on your system. A little technology recap, part 2, so to speak, is just agnostic to whatever container technology you're using, whether it's Rocket or it's Docker or whatever else. In the kernel, we have 3 ingredients, 4 maybe if we want to extend it a little bit. But the main ones are kernel namespaces, and kernel namespaces are just somehow an Excel sheet of different resource allocations. So, for instance, there are 6 or 7 namespaces now. I think the easiest one is the PID namespace. So if you are all familiar with Linux, right? If you type ps-ef or whatever arguments you fancy, then you will see a process list of all processes that are in your namespace. And if you don't use containers, you only have one namespace, so you will see all the processes on the host. You will see the process ID, the parent, the binary, and other different details. So this is the list of resources that are currently on the host in terms of the process ID. And there are other namespaces like the network namespace, which gives you an interface, like a network interface, IP addresses, routing, ARP tables, and so on. And when you start a container, the container engine will provide you with all the namespaces for each and every container that you have started. And this looks and feels much like a virtual machine, even though it's not, but it feels like a virtual machine because you are isolated from the rest of the system, so you cannot see other processes, you cannot use shared memory to communicate with other processes because you are isolated due to namespaces. Where this notion breaks a little bit is when you start share namespaces. So this is obviously not possible with virtual machines, but containers you can start so that they use the network namespace of the host, so they have the same network interfaces, they have the same IP addresses, the same host name, and so on. And you can do this with other namespaces as well. And this is little spoiler alert. This is what's used by Kubernetes in this pod concept. And I don't want to get too much details, but what's essentially happening is you have a web server and you have a database server in this little stack that Kubernetes is using to schedule resources. And there's one container that doesn't do nothing. He just creates all the namespaces, and on top of that, you can put as many processes with different containers as you like. So you can talk over localhost or with shared memory because they are all in the same namespace. But that's a little spoiler. Namespaces just isolate. So if you create containers on host, then they can consume all the resources they like. They are just processes on the host kernel, in essence, right? And what we see here is I have this stress command in a container, and the first container starts, it gets all the resources that are available to the container, and this is what you would have if you don't constrain anything. What I do here is I constrain the container to only use the first core, so the 0 core. So it's only consuming 100% CPU, even though it tries to leverage or to consume 2 CPUs. And I have 2 CPUs in this system, but since I only pin him on the first CPU, the process can only be scheduled on the first CPU. So hence, it gets only 100%, up to 100%. When I start a second container, then normally they will level out by 50% each because they have the same privileges or the same shares. And when I provide a CPU share argument, I can give different weights to different containers. So we see that the first container is 100%, I start the second container, and then they level out between 66 and 33% because they have different shares. So 1/3, 2/3. And this constraint can be applied to CPU, to memory, to network I/O, to block I/O, and all the C groups that are in the kernel. And yeah, this is what's used by all the container runtimes out there. And this is not something that Docker invented, obviously, right? We are on the shoulder of giants here. So all the networking, all C groups and namespaces, it's just used by us and used by everyone. And we are just summing it up so that it's easy to use. Another thing that's essential for the rise of containers, so to speak, is overlaying file systems. Normally in virtual machines, if you want to transfer a virtual machine to someone else, you have to dump the complete thing and then you send over the complete system, right? With containers, you have layers of file systems and they augment each other, they are squashed together, and then you have your running container. So when you assemble a container like this, we inherit from Ubuntu 16.04. This guy has like 100 megabytes, more or less. And when I run this apt-get update command, I add another 150 megabytes to this previous layer, and then installing libcuda into another layer, I add a little bit over 1 gigabyte to this container. And this container then has the effective size of 1.5, more or less, gigabyte, but it's assembled out of multiple file system layers. And if I want to install a new CUDA library, for instance, I can reuse the 2 layers below and just add another layer that is different from the other 2. So if I have 50 different images using the same layers underneath, or if I add a big file as a layer into the container, I can, in whichever image I use the same layer, I don't have to duplicate the data because it's already there. And this green boxes, together with this blue box, which is just the metadata, the configuration of the container, constitutes the container image. And by starting a container with Docker run, for instance, what I do is I take this image with all the layers, then instantiate, so extract basically the tarball, which is how the container layers are stored, the image layers are stored. I extract it into a file system, depending on which storage driver I use. Let's say it's overlay 2. So I create a file system that creates a file system that is like the essence or the merger of all the different file system layers in the container. And when starting the container, I create a very thin read-write layer on top of this read-only layers, where I can touch files in and I can diff the files that are in the container changed when I started it and changed during runtime. And this is what we see here in this docker diff command. So I create a file, root test.txt, and when I exit from the container, I can see that I changed the bash history because I ran a command, right? And then I created this test.txt file. What Alberto, was it Alberto? Alberto, right? Alberto talked about that Shifter is using read-only kind of file system, right? You cannot change the file system of the container. It's also possible with Docker as well that and I would think that this is best practice, by the way, for HPC workloads or for all the workloads, that you create a container that has no read-write layer so that you cannot change files within the container by accident or by malpractice. So when you do this with read-only, what you do is you create just this read-only piece of the container and you don't create this read-write layer. Yeah, the fourth piece is security. By default, we have seccomp, which is part of the Linux kernel, right? So namespaces isolate, control groups constrain the resource use, and seccomp filters constrain the syscalls. Because we are running under the same kernel, imagine you can do a power off within the container. That would be kind of stupid, right? Because then you would power down the machine. What is mapped is that if you do power down within a container, it will just exit the container and not power down the machine. And there are a couple of sane defaults in our seccomp profile that we deliver that just prevents bad things from happening. But this is also only filtering syscalls, right? So there's SE Linux and Apermore where you can do more than just syscalls. You can filter on file access and various other things. Okay, this is the Linux technology, or this was the Linux technology that enables containers. And if you grab containers, by the way, in the Linux kernel, you won't see it, right? So containers is just a name for the summary or the conglomeration of these techniques. What we did to create something that one can use is the architecture that we have. Very bottom down is runc. Runc is a command line tool to spawn container images, which are complying with the OCI runtime specification. So OCI is the Open Container Initiative, and it has a couple of things you need to implement, like C groups, like seccomp filters, and so on. And when you use runc, it's very much plumbing. So you have a root file system. This is like a directory where all the files reside that you want to have in the container. You have a little config JSON that provides you with information as to how to start the container. And then you use runc, and you have an interactive container at the end. So this is just a command line interface tool. And if we compare it with Shifter and Charlie Cloud and Singularity, this I think is more or less the good comparison point here. Shifter and Charlie Cloud Singularity, what they do is, and Alberto already touched on it, they download the Docker image, extract the file system, squash it into into an image that you can put on a shared file system, and then execute a process within this root file system, right? So more or less what's here. The thing is that Shifter, Charlie Cloud, and Singularity, they are all not OCI compliant, so you cannot create a new user or a different user. For instance, you cannot use seccomp profiles and so on. And I mean, that's fair because it's not the goal of this runtimes to be OCI compliant, and in most cases you don't want it to be. I mean, you want to run a user-land container, so to speak, right? You want to run under the same user ID, under the same GID, and you want to have the same privileges as the user. So that's super fair. But that's just saying that it's not OCI compliant, because what comes level up or a layer up on top of runc, we have containerd, and containerd is used to download images, to extract the images, to create this root file system, to spawn a container, and this hooks then, or there is the runtime that is used. In this case, I put the runc logo, but it could be Rocket or so on. So containerd is just a minimalistic daemon that is able to maintain the state of a container and create a container and put events up to be gathered. So it's a very simple implementation of how you can start containers and run containers on a node. Okay, so this runc and containerd, and this then already almost constitutes what is used to create containers. So on the bottom here we have control groups, namespaces, and layer capabilities. And in between runc and containerd, they provide the means to create containers and start containers. And on top of this gRPC interface that containerd provides, we have the Docker engine that is able to start a container, wire up the networking, create volumes and such, and with plugins you can even extend it a little bit more. And this is the means of creating containers. So if you do Docker run, you hit the REST interface of the Docker daemon, and then the Docker daemon will instruct containerd and runc at the end to create a container. And again, like a little comparison or a little glimpse of where I would think I would put Shifter, Singularity, and Charlie Cloud is like here. It's a little bit more than runc, obviously, because it can download images and it can extract images. So it's also a little bit of containerd. So that's where I would put it. And by the way, we can all disagree. I'm very open, like just my glimpse or my take on it. On Windows, it looks quite similar, even though we are not a Windows community, I think, but just as an idea, or maybe if you think about a workload that you have on Windows, you can also run Windows containers now. With Windows 2016, they introduced the equivalent of control groups, namespaces, and layer capabilities, and they put a service on top of it so that you can interface with it. So now you can even run your ray tracing application or your post or preprocessor in containers, and you don't have to mess up your Windows installation anymore. So that said, that's the basic recap of the technology. Now I would like to talk about the challenges that Docker has or containers in HPC have. And this is where we talk about host agnostic and host specific containers. And this is where cloud clashes with clusters or with tightly coupled workloads or host-specific devices and technologies. And this is where the basic foundation of the, I won't say disagreement, but the different understanding of such systems is, right? So in the cloud, you want to be host agnostic because you want to port your application to different cloud vendors, to different architectures, and you don't want to be concerned about where you want to run it. So that's where Docker is really, or used to be very closed in terms of making host-specific decisions. So, but what we need in HPC is to be able to run on shared resources, right? For instance, the simplest shared resource, and maybe the most important one, is shared file systems. So you don't want to run, when you create some data or when you compute something, you want to read and write to a shared file system, and you want to do so securely. And also, if you want to have intermediate results displayed by a web server or maybe a little JavaScript that you created, you also want to be sure that the service that you created in order to display your data has only access to the data that you are supposed to access, right? So what needs to be done is to pin the user to whatever user was calling the job, right? And this is what Charlie Cloud, Singularity, and Shifter are doing, right? They create a container that is under the same privileges, under the same user than the user that's calling it, because it's in the userland of the container. So this is a given. And for Docker, you can tamper with this user normally, right? So if you create a user, or if you run a container like this, so I mount in the home directory, like the root of the home directory, and then Bob is saying, okay, give me the user ID and the group ID of Alice, and he creates a container that is under the same user ID and group ID. The process within the container is forked under the same user ID and group ID than Alice. So he can just write into the home directory of Alice, and the file was created by Alice, because the user and the group is essentially Alice, right? So this is the bad example, but it's like it was designed, right? It was host agnostic, and this should not be trusted anyways, so you should not mount, normal case, you should not mount something where you rely on the user ID and group ID into the container. What has to be done, and this is a prototype I did in November to showcase it internally, is it should be that the Docker engine checks who is running the container or who is starting the container, and then overrides the user flag according to what user was running the container. And then we are at this little diagram, right? When Alice is starting a container, she can do whatever she likes with this -- user flag. It will be overwritten by the engine so that it's the user that is outside of the container is also inside of the container, and this will then prevent something bad from happening. So when I do this, my little proxy detects that the user tries to post as Alice, and he just overrides it with Bob's user ID, and then you are not allowed to access the home directory of Alice anymore. And also what's going on here is I can provide mounts that I want to be present in the container, because if you are a user of an HPC system, you have certain assumptions that you think are true on all the systems, right? You log into a system, you have your home directory mounted already, you have your shared file systems like the project or the Scratch file system mounted already, and you should not worry about what should be mounted on the particular system, because you don't know, right? If you're scheduled on cluster A, there might be different mounts to be mounted than on cluster B. So it should be a host-specific configuration as to what default mounts are present in the container. And by doing this, we have this shared environment thing handled, and the kernel can make sure that the user, the POSIX ACLs are honored and complied, and so we can use shared file systems with raw speed, right? Because we just bind mount a directory, it will be raw speed. Second thing that's very important is We need to allow kernel bypassing devices, also host specifically created and mapped into the containers that are willing to use it. So for instance, if I have two hosts, one with slightly different GPU and a slightly different CUDA driver that needs to be present, or you have MPI and you have an InfiniBand device and you want to map in OFAT and the MPI that is most tailored to the device that you want to map in. That has to be done also automatically in the same fashion that I mounted the homes and I forced the user ID. So the Docker engine on the host should make this decision as to what device is mapped in and what CUDA version is mapped in. And this essentially was NVIDIA Docker. They have some other tricks that they do, and I guess maybe Axel will talk about this. There he is. So they make some other different things, but in essence, that's what needs to happen, right? You need to map in the NVIDIA device, and you need to map in the CUDA driver, and then you can use CUDA. So the same little proxy I created, but with slightly different options here. So I tell my proxy that I want to run with GPUs, and I also tell him where to find the CUDA driver on the host. So we saw this earlier that the CUDA driver is pretty large. So if you create a container that has a rather small binary, and you have to add 1 gigabyte just to have CUDA packed within the container, that's rather inefficient. So what I'm doing here is I create a normal Ubuntu container and mapping in the CUDA library from the host, the same way as said, NVIDIA Docker is doing as well. And I map in some devices, which are mapped in by the little API proxy. And when I start this container, I can use the CUDA NVIDIA SMI binary to just use CUDA as it is supposed to be used. And the same applies to InfiniBand here, and maybe even TPUs, I'm not sure, but everything that is kernel bypassing needs some devices and some driver, right? So that's the same approach. And what we could do with this, and I'm pushing internally to make this a thing, is that we can combine the workload. So currently we have the Docker engine or container engine that is handling, that's not handling shared systems, and you create processes in isolated namespaces constrained by C groups and secured by SecComp, but you create the processes under or with the help of runc on the host, and you don't have secure access to the shared file systems, right? On the right-hand side, we have slurmd or whatever workload scheduler you fancy. They create a process on behalf of the user with user permissions and the user environment, and they are able to use the shared systems because they are not isolated by namespaces, right? So, and this also is a slide to convey the message. People are hesitant to use a container engine because they think there is a daemon running as a root in privilege mode who is able to start processes on behalf of another user. I mean, that's what's going on in HPC for a long time now with HPC scheduler. So I think it's a rather flawed argument. Anyhow. But this is what the current state is, and again, just placing the HPC runtimes. They are wrapping around the job process, right? So Slurm is not executing the job process directly; he's just wrapping it into Slurm or Shifter or Singularity or Charlie Cloud. And with the changes that I displayed, what could be happening, or what I hope will happen, that no matter if you have fancy new AI workloads that are coming out of the Kubernetes community, or you have your HPC workload scheduler, normal scheduler workloads, you can just underpin everything with a Docker engine, and depending on what workload you have, if it's a service or it's an HPC job, it will be either put into the shared system securely or it won't. So you can underpin everything with the Docker engine and don't have to worry about forking a process anymore. I mean, then all the workload schedulers, they can go up the abstraction a little bit, and they don't have to worry about starting processes anymore. They can just interface with the Docker engine, but again, a little bit biased, obviously, and start containers. And this slide I added last week, and thanks for Torsten for the introduction. This is, I think, a little bit of the journey, the journey you will go through if you use first simple GPU workloads, and if you go up and up the complexity, you will end up having full-fledged HPC workloads at the end. So what do I mean by this? And by the way, I'm not yet an expert on AI, so, but Thorsten said, yeah, it's close to reality, what I'm about to show. So thing is, when you start with GPU usage, you stay on one node, right? So you have a single node deployment, and you somehow have the storage figured out. Maybe it's a simple storage that is just localhost, but the job stays on one node. And the data transfer is maybe handled outside of the container, or if you use NVIDIA Docker, you maybe stage the data beforehand and then have a directory where you can access the data. Or the data is mount read-only for everyone anyways, because it's almost public data, and you can just fetch the data and you don't have to worry about POSIX ACLs that much. Process here that it's pretty much host agnostic, so in Kubernetes they have GPU support now, and it just assumes there is a GPU, and the kubelet will propagate whatever GPU is there, and then the scheduler can make decisions, so it's rather, it's convenient to use, and you don't need to worry about POSIX ACLs on shared file systems, and but the drawbacks are is that you have to write back the results in some fashion, so maybe it's a post job again, you write into a local directory, and at the end you copy it back to the shared storage. And if you need to scale, you need to put a lot of money on the table. The recently announced DGX2 costs you like almost $500,000 to have this 16 GPU monster, I think is fair to say. So if you want to scale, you need to have money. If you want to have a shared file system where you also put the data and where you have different ACLs for different directories, it's becoming a little bit more complex. So you still have a loosely coupled, or you have multi-nodes, but they don't exchange any intermediate results. They just feed from the same source, but they have their own result set and their own model partition that they feed. And you feed it, as said, by a shared file system. You're still somewhat host agnostic because you don't, you have an assumption of a GPU is present, but no further things. And you don't have a central model, so you don't need to exchange information. But you still need to honor the shared file system. And I'm not sure, I mean, maybe that's a discussion to have how this is solved currently. I think there's no easy way to fix it. If you have a shared file system, you somehow may have to mount the directories for each container with the credentials of the user, but you cannot just mount in /home and then be sure that everything works fine. And even worse, if you want to have a data parallelism, so you want to exchange information of the weights for different partitions of the input data with the same model, you need to exchange this intermediate results somehow. And there is, for instance, Spark ML, which uses RDMA to put the updates to the parameter server somewhere, or there's also a TensorFlow MPI implementation which does this with MPI calls. But you need RDMA access, so you need to have InfiniBand or OmniPath or whatever present, and you also need to honor the shared file system again. So this is where we arrived at an HPC job, right? So you have shared file system, you have a tightly coupled multi-node setup, and voila, we are arriving at HPC. So that's what we all know, right? So this is my little 3-step GPU to HPC piece. Okay, so now a little outlook, what I call high-performance containers, because the acronym is the same. But what we want to achieve this year is to have like this tentative milestones achieved. So first what we need, and this I touched on before, is secure operations in shared environments, in particular pinning users so that you can use shared file systems. Second, transparent support of kernel bypassing devices so that you can use GPUs and InfiniBand natively. And once this is fixed, then we have the basic implementation that is needed for containers in HPC. And then we can look into integration of HPC workload schedulers. So as we all know, MPI setup, it's rather a complex endeavor, right? You need to have the correct PID. So there's a lot of MPI things that you have to consider in order to make containers in HPC also a thing. There is PIMX, which might help if it would be implemented in the Docker engine so that it's a PIMX server. That would be helpful. But anyhow, there's a lot of things that needs to be done. But first we need the first milestones anyhow. And also what's important for some systems, that you need to support diskless nodes, and you don't want to run, not even only particular to diskless nodes, but imagine you have 5,000 nodes, they all download the same image at the same time, and they all put the tarball, so the different files, on their local storage, then they extract the file system to create a container. That's a lot of overhead that won't scale infinitely, right? So what would be much, much nicer is that if you have a shared file system, that you download the blobs once, you put it once on the shared file system, and every container engine on all the nodes can reuse whatever one node has put there. And also, if you extract the file system to instantiate a container, it's also should be pretty nice to just extract it once, put it on the shared file system, and all the containers of the same kind, they can use a shared file system, and you don't need to extract it multiple times. And this would fancy like distnet nodes as well. And yeah, so these are the four, I think I would like to focus on the first pieces of milestones because this is the most important, the rest will follow. I'm coaching a student cluster competition team this year. So, I mean, we have the HPC Advisory Council meeting, right? There is this student cluster competition upcoming at ISC with 12 groups, right? And yeah, I'm coaching the Hamburg team. First goal is to use containerized auxiliary services like monitoring, logging, and such, and inventory. Let's see what we can throw in there. Which is cool and which is, I think, very much what's needed as well, but that's the rather non-HPC boring part because it's just cloud software stacks, and with Docker we know a lot of cloud stacks, so that's it's exciting, but it's still for me a little bit more boring. What I would like to see more is this prototype of the changes that I described, so that we can show how to use containers in an HPC environment with a little example. So if you are at the ISC, I hope you swing by the booth and say hi to the guys and see what can be done with containers. And if you want to get involved, I mean, if you're already a customer of ours, then just push for HPC and big data use cases at your sales rep. If not, then become one and do the same thing. And if you don't want to become a customer yet, then just enhance your skills and container knowledge, which you might already do by using Singularity Shifter and Charlie Cloud. I mean, that's the first step. And I don't blame someone who's using it. I mean, there's a lot of space for everyone. And yeah, just get yourself involved, get yourself educated about containers, and then once everything is compiled, we can all like hit the floor running. Yeah, in midterm, long-term goals, there are a lot of, I mean, the more I think about it, and I think about it like for 4 years now, I said, there's a lot of stuff that can be done here. I mean, reproducibility for starters. You can have a paper published that fancies or that shows the container with the content hash so that when you download the container, you are sure that you have the exact same file system than the guy who created the paper, right? So you don't have to worry how is it installed or whatnot. So you just download the image and you can have the same thing. Also, like Alberto managed, like the Docker file, the recipe helps you to foster collaboration because you can just download an image from someone who had done a paper or who had done some research, and you piggyback on this image by adding your own little piece of library or your own input deck, and you can make sure that you have the same baseline. And what I'm really thrilled about for a long time now, and this was maybe the second interview I did with Rich, was optimize the user land, and this is what I'm looking forward to very much. So imagine, as I said, we don't have to make any assumptions or we don't have to take anything else into account than the application we want to run. And by having this, you can just hand tailor all the libraries, all the BLAS and all the MPI libraries that you have just for the container, because everything is bundled up. You can optimize this. And this is going to be, that's going to be a gold mine alongside with automated optimization, so having an optimization job that runs overnight, permutates all the different packages and configuration and input decks, and optimize the workload for you. And there's a couple of other things, like if you use our platform, then you have image scanning, image signing, and CI/CD all for free, so that if you import an image as a user and you don't have the signature that is granted by the operations team, you cannot run the container. I mean, this is also something that for bigger clouds or more open environments might be is very useful, that you can constrain the images to be run, and so on and so on. So there's a lot of stuff that that can be done, and it's not even. I mean, I have a long backlog and laundry list of things I would like to try out. And that would be about it. So I'm around until Thursday evening. So if you want to engage, just talk to me. I'm very open for everything. And yeah, any questions so far? Then I'm happy to answer it.